Hey guys, welcome to the tutorial of the MSPPy package. In this series of videos, I'm going to briefly go through some of the key features of the package, and I'm going to show you examples on how to use the package. If you've never heard of MSPPy and if it intrigues you or you want to find more details, you can visit the GitHub page or the documentation page for the package. You can also read our papers. There are so far 2 papers about MSPPy, so I will put all the links in the video description below. So let's get started. Just to refresh your knowledge, here is an introductory example, which is the classical news vendor problem. Later on, I will also use this example to show you how to use the package to actually solve this problem. Okay. So the problem is the following. Every morning, a news vendor purchases newspapers from the publisher and sells them during the day. So how should a vendor decide how many newspapers to order every morning? So this problem can be modeled as a classical 2-stage stochastic program. Essentially, in the first stage, or in the morning, before the real demand is known, so we denote demand by a random variable Kasi here. So before Kasi is known, we need to make buy orders. So we use X to denote how many newspapers we purchase. And then in the second stage, or by the end of the day, we observe the realized demand. And we sell and recycle certain amounts of newspapers during the day. Those numbers are denoted by Y1 and Y2. So on the top, you can see it is the so-called extensive formulation of the 2-stage problem. Okay? The objective here is to minimize the cost or maximize the profit if you flip the sign. But I will stick to minimization problems during this presentation. So the objective here is the wholesale cost. B here is the unit wholesale price of the newspaper, and times how many newspapers we purchased, and minus the S times Y1. S here is the unit retail price, and the Y1 is how many newspapers we sell, and then minus the R times Y2. So R here is the unit recycle price, and the Y2 is how many newspapers we recycle. Okay, so this is the objective, and we have some constraints. The first constraint is saying that the number of newspapers we sold should be less or equal to the demand. Okay, and the second one is saying the number of newspapers recycled plus the number of newspapers sold should be less or equal to the number of newspapers purchased. Okay. And all those decision variables should be greater or equal to 0. So this formulation is very straightforward. So on the bottom, it's using the DP language. Essentially, it's the dynamic equations of the problem. So the total cost is decomposed to a first stage deterministic wholesale cost and a so-called value function, CalEQ, or the expected cost to go, if you will, which is the average of the optimal costs or profit, if you flip the sign, for average subproblems in stage 2, as shown here on the bottom right. So here X is the so-called state variables because it links the 2 states, all right? And all the other variables are the so-called local or control variables. Okay, so those includes Y1 and Y2. So this is kind of a toy example. Now, for a general multi-stage problem, we'll have a data process Kasi to be revealed over time, and the decision we make should adapt to the process. In other words, the decision should be a measurable function of the underlying data process. So here I make this x bold, just to remind you this is a function of the underlying data process. So this chain here represents a sequence of actions and observations. We always assume the first stage is deterministic. In other words, Kasi1 is no. And the sequence of decision variables x1, x2 to xt are called an implementable policy, or just a policy in short. We also have some feasibility constraints, cost functions, and a discount factor. In the end, the objective is to minimize the total discounted cost in some risk measure over all implementable feasible policies. So the expectation here can be replaced by a nested risk measure, but I will stick to risk neutral measure in this presentation. So finally, we always assume the relative complete recourse condition, that is, for whatever the past state is, for almost all realizations of the data process Kasi, we can always find a feasible solution of the current state variable xt. Okay, so this is the general setting for multi-state stochastic programs. So the package mostly focuses on multi-state stochastic linear problems, or MSLP, which means that the objective function and the constraints are linear with respect to the decision variables. So the data process we consider is either stage-wise independent or Markovian. And we assume the probability distribution of the process is no. So the data process is the so-called exogenous process. Okay? So for example, the data process can follow a log normal distribution if it is stage-wise independent, or it can follow an autoregressive process if it is Markovian. All right. So here are two kinds of notations. One is sort of canonical form, which is a concise way to model an MSLP, especially when developing theory. So we have a state balance constraint here, okay, and shrink all the other local constraints to a closed set Cayley X. All right, and the cost function here is ut times xt, which is a linear function. Okay, and we don't distinguish between control variables and the state variables. We combine them into a single decision vector xt. All right, and the other formulation is more explicit, which unfolds the data process into stage-wise independent and Markovian. So we denote stage-wise independent process by Kasi t, and denote Markovian process by eta t. And we also decompose the decision variables into state and control variables. All right. So the xt here is the state variables, and the yt are the control variables. In addition, we have an additional variable zt here being the local copy of xt minus 1. So that the state balance constraints are reduced to zt equaling xt minus 1. All right? And all the other constraints are formulated using this matrix-like constraints. All right? And you can see the cost functions here have two terms. One is related to the cost of the state variables, and the other is the cost of the control variables. Okay, so this so-called matrix form is more convenient for implementations, and also for other reasons as well, as we will see very soon. So MSPPy adopts this matrix form here. And here, the stochastic process Kasi t, eta t are assembled from UT, VT, capital AT, BT, CT, and right hand side BT. So essentially the uncertainty can appear anywhere. All right. So this is the formulation. So here on the top, again, it's the matrix form of the MSLP. And by exchanging the minimization and expectation and using the law of iterated expectation, we have the following equivalent nested formulation. All right. So this nested formulation actually suggests a way to write dynamic equations. For stage-wise independent problems in which we only have Cauchy and not eta, the value functions here do not depend on Cauchy. So for every stage, we have one single value function which is convex with respect to x. And the subgradients of the value functions Cal EQ are given by the subgradients of all q, where each q is the optimal value for each subproblem in the next stage. All right, so here you can see another reason for including this local copy variable zt. That is, the subgradients are now exactly those dual solutions. Okay, so this is the stage-wise independent case. For Markovian problems, we can have both stage-wise independent Cauchy t and a Markovian process eta t, as long as they are independent. In this case, the value functions are now depending on the current value of eta t rather than the whole history, and the value functions are not convex with respect to eta t. So for each stage, we need to keep one value function for each Markov state in memory. All right, so that's pretty much it for the background of the multi-stochastic programs. In the next video, I'm going to show you how to solve such problems.